All right. Well, welcome back. You all doing okay? Let's start with a discussion, then I'll answer questions over homework after that. Um, our first test is scheduled for a week from today, next Wednesday. It's supposed to cover all of Chapter 1, and the plan is to have the test a week from today. So I don't look at us pushing that back at all. I've been asked about whether or not I give out a review for the test. Yes, I will give a review. What I'll probably do is put it out on the Canvas, in your Canvas course under Files, sometime maybe on Friday. So I'll work on it in the next day or two and then put it out there on Friday, and you can kind of have it for the weekend to take a look at. And then when we come back on Monday, I'll have to finish up some material and then well, yeah, that was the next thing I'm going to talk about. In the calendar, it says today we're supposed to cover 1.5. That's what it says here. I know probably after the last class, and I gave that quiz, I bet you a bunch of people watched 1.5, right? We as a class need to make a decision here. I can do 1.5, which is continuity, and we can talk about continuity. There's a lot in that section, but there's not a whole lot on your test on that section. So I am kind of leaning towards doing 1.6 today. That way you have 1.6 kind of before you start the review. Would you prefer I go in the order, or would you prefer I show you the stuff that's going to be more on the test today? More on this? Of course. Okay. So, but we will cover 1.5, all right? And I'll present 1.6 today as if you didn't watch the video, so I'll be kind of thorough with it, all right? Okay. Any questions on what I just said about test next week or review? If I have not sent something by Saturday morning, then someone send me an email. I know everyone will send me an email, but someone say, hey, where's the review, you know? Okay, so my plan is to have it out there by Friday night. Now, I don't have an entire class period dedicated to reviewing for the exam. Like, I will give you a review, but I'm not going to, you know, we're not going to come in next Monday and be like, okay, let's review for the test. The review is you have done your homework, and the review is you've looked at the review I've given you, and you've worked through those, and you feel comfortable with those problems, and that's the best way to review. All right? Questions on homework? Number 14? Okay. Oh, yeah. That's right. I did say you would struggle with those, and you did, apparently. That's good. Struggle. So you want me to do 14? 14? 14 is, wait a minute. Am I looking at the right section here? 1.4? I thought we did 14 in class. Oh. So what's wrong with 14? This one? Ah, okay. Yes, I know why. Well, we're going to talk about this today. This is part of what today is about. I don't like the fact that the book gives this problem so early. It introduces you to this, I think, too soon. What happened when you plugged in direct substitution? What did you get? 5 over 0? Is that what you got? But when you do algebra on the top, you get x times x minus 4, and then what is the bottom factor to be? X minus 4x plus 1? Is that what you got? These cancel, limit, x approaches -1. Oh, okay, I see it now. And so when you plug in -1, you still get -1/0. And there's nothing else you can cancel, right? So what the book says at this point in this chapter, in this section, is whenever you get a fixed number on top and 0 on the bottom, we're just going to say does not exist. We're just going to say does not exist. But today, we are actually going to have an answer for this. All right? So I don't want you to even think about does not exist at this point, all right? Let's just leave this as a question that we will answer today. 27? I did 27. Didn't I? Oh, is that a cubed? Oh, that's cubed, right? Working quickly. Limit h goes to 0. Whoa. Did you expand that out? X plus h times x plus h times x plus h? Who asked me? You got what? That's correct. Who asked me about this one? Okay. So did you expand out x plus h cubed? Did you do it 3 times? Did you get x cubed plus 3x squared h plus 3xh squared plus h cubed? Then you subtract from that the x cubed that was still there. Is that what you missed? And then you had the h down here. So that x cubed cancels, and then everything has an h in it. Just forgot that x cubed out there? Okay, good. Quick fix. Anything else? All right, let's go to 1.6 then. We are going to be talking about limits, still talking about limits, right? Last class we spent all of our time saying, what happens if we get 0/0? You know, then we're going to come in and do some algebra or some sort of trick, right? Something, factor, what else did we use? Conjugate, right? Different things. Now what we're going to do is look at limits that involve infinity. So we've already seen sometimes we get infinity or negative infinity. We have not seen that. I showed you once that, and this was in the very beginning of class, we talked about this. Remember we were talking about power functions, like these are the functions everyone should kind of know what they look like. And we were talking about like 1/x squared. It looked like this. As you approach 0 on the left side, it goes up, and we said it goes up forever and ever and ever, right? It keeps on going higher and higher to where? Infinity, right? That's up there, infinity. And then if we come in on the right side and we go towards 0, it's going to go up and up and up forever again, right? So we would say that our function is like approaching infinity that way, right? Yes? So does it make sense to say limit as x approaches 0 of 1/x squared would be infinity? Yes? So how about this one? This example right here. Limit x approaches 0 of 1/x. Not 1/x squared, 1/x. Here's the graph. What happens as I approach 0 from the left side? It goes to negative infinity, right? What happens if I approach 0 from the right side? It goes to positive infinity. So look, as I approach 0 with that little negative up there meant from the left, right? So as I approach 0 from the left of 1/x, it goes to negative infinity. I'm going down forever. As I approach 0 from the right, it goes to positive infinity. So if I say, what's the limit as x approaches 0, and I do not specify left or right, that means you have to compare the two, don't you? And you have to say, are they equal? So is positive infinity the same as negative infinity? No. So we say it does not exist. So for a limit to exist, it has to be the same from the left and right. If one side goes to positive infinity, the other goes to negative, or the other way around, the limit doesn't exist. Why did it exist here? They're both going to positive infinity. So if they both go to positive infinity, both sides, the limit goes to infinity. If they both go to negative infinity, it would go to negative infinity. Is that a question? Yeah, I did mention that. We all decided as a class to cover today the section that's going to have more problems on your test, and then we'll come in and we'll do 1.5 on Monday. So you're not in trouble for not watching 1.6 because I didn't assign that. I think 1.6 is way more valuable to you at this point than 1.5, or yeah, 1.5 would be. Okay. Now notice on both of these graphs that back in college algebra, we would have called these vertical asymptotes, wouldn't we? We called them vertical asymptotes. So we have a definition. We say the line x equals a. X equals a is a vertical line. We call that a vertical asymptote if one of these things are true. As we approach a from the left, it goes to infinity. We approach a from the right, it goes to infinity. Or from the left, it goes to negative infinity, or from the right, negative infinity, or infinity from both sides. So anytime we have that action going on, right, that's a vertical asymptote. Yes? That's the way it looked in college algebra. I will abbreviate VA for vertical asymptote. So let's take a look again at this graph. We have the vertical asymptote at 0, right? So x equals 0 is our vertical asymptote. This one, again, x is 0 is our vertical asymptote. See, the vertical asymptote doesn't care about, like, it has to be the same from both sides. The vertical asymptote just says, coming from one side, I'm pushing the function down either to negative infinity or pushing it up to positive. If that happens on either side, it's a vertical asymptote. Questions? Everyone understand the visual of what's happening here? Okay, take a look at this graph. In this graph, we notice that the limit as x approaches 2 of f of x does not exist. So why is that? Here's 2, right? 2 is like a vertical line right here. What's happening as I approach that from the right? I mean from the left, sorry. Switch this. I'm going to try and draw a line down the center here. That's not a very good line. Oh, close. That's x is 2, right? So I come in from the left, what happens? Goes to infinity. As I come in from the right, what happens? It looks like it's approaching that value, right? And that looks like maybe 1, somewhere around there. So the limit doesn't exist. Why? They have to be the same from both sides, right? So the limit doesn't exist. However, we still have a vertical asymptote, and the vertical asymptote is x equals 2. Because the definition of vertical asymptote says you just have to go to infinity or negative infinity on one side. If that happens, you're good. Make sense? Okay, limits at infinity. Don't confuse this with infinite limits. All right, so far, what we just looked at, we've always, in every limit we've always looked at, we've always let x go to a number, right? Like x goes to 2, x goes to 0, x goes to 5. All right, now what we're going to do is do these things called limits at infinity, meaning we're going to look at what happens when you let that x go to infinity or x go to negative infinity. So here's the notation we use. X goes to infinity or x goes to negative infinity. So we're going to start with this example. We, again, talked about this way in the beginning. When I say what happens as x goes to positive infinity of this function 1 over x, I'm saying how does the graph behave as x gets bigger and goes out to the right forever? Right? Infinity is that direction. X value, infinity is that direction. What's the function doing as I go out there? It's getting closer to 0, right? In fact, I'll zoom in. As x goes out to, notice my x value is changing here, right? I'm going out. Can you all see I'm out at 81 right now? I'm going out. Look at my function's value. It's getting closer and closer and closer to 0, right? Closer and closer the further I go out. So as I go out to infinity, the graph is getting closer to 0. So does that make sense that this would be true? Yes? Now, what happens if I go the other way, negative infinity? Now I'm going to be going out the left side, right? Going out this way to negative infinity. If I zoom in on that, I'm getting closer and closer and closer to 0. Now, they're getting closer to 0 through negative values, right? Those are negative numbers, but they're real small. So either direction, I'm going to 0. And then what we get is our first major, idea formula that we need to make sure we're all comfortable with. If n is any positive integer, then the limit as x goes to infinity of 1 over x to the n, or the limit as x goes to negative infinity of 1 over x to the n, both go to 0. Now here's the way I want you to understand this. I think this will make more sense hopefully it'll make more sense to you. What if I gave you a fraction 1 over 10? Everyone's comfortable, 1/10, that's a small number, I guess, 1/10. But if I let the bottom get bigger, right, the bottom gets bigger, 1 divided by 100 actually gets smaller, doesn't it? So this is actually smaller than that. And then if I let the bottom get bigger again, let's say 1,000, that's even smaller, right? And so it keeps getting smaller, and eventually this is approaching 0, isn't it? So if you have a fixed number, and you divide it by a number that is infinite. Now, I'm using very, very loose notation here. Infinity is not a number, all right? You can't quantify infinity. 10 is a number, right? 10 is a number, 100 is a number, 1,000, 10,000. When I write down fixed over infinity, what I mean by that is your numerator is stuck at a number, like 1. And infinity means the bottom's getting larger. Understand? What happens when you have a fixed number and the bottom gets larger? No matter what should happen? It should go to 0. Okay? This should go to 0. This is something, as a calculus student, I want everyone here to understand. That's a major concept. Fixed number, doesn't matter what that fixed number is other than, yes? It's not changing, right? So like that numerator up there is not changing. It's 1, 1, 1, 1. But the bottom got bigger and bigger and bigger. The fractions get smaller and smaller and smaller that way. And they approach 0. Nope, does not have to be positive. All right? Are we okay with that? I'm going to summarize all this later. So here we're going to look at, I think I'll give you a couple more examples before I do that to you. So what about this? As an example, let's find the limit as x goes to infinity of 100 million cajillion gazillion over x squared. That's not a million cajillions, whatever I just said. It's what is that? Trillion? 100 trillion. Billion. Yeah, billion. Sorry. What is this limit? 0. Why? The numerator's fixed, right? It's a big number. And if I plug in, let's say 1 for x, this is going to be huge, isn't it? Right? Plug in 1, you get 100 billion divided by 1, which is 100 billion. But that's not what they're asking. They're saying let x get bigger. How big? Let it go to infinity. So what happens, even though the top is big, the bottom is going to get bigger and bigger and bigger and bigger. Eventually, it'll be bigger than 100 billion. So much bigger is squash it down to nothing. Yes? So this should be 0. Now, according to what the formula in the notes say, this should happen no matter what's going on up top. I'll just put e to the e to the e to the e to the e over x to the fifth power. E to the e to the e to the e to the e is just a number, isn't it? All those are just constants. You could have said 2 to the 2 to the 2 to the 2 to the 2. That's just a number. Over x to the fifth, if x is getting bigger, then this should be 0. Because again, I have a fixed number on top divided by a number that's getting larger on the bottom. Now, does that help you see what this is saying now? Yes? If I have the limit as x goes to infinity of 1 over x to the n, that's 0. Or negative infinity, because it doesn't matter. Infinity or negative infinity, it's getting bigger, right? So it'll squash the thing down to 0. The fact that that's a 1 really doesn't matter, because if I had a constant like 100 billion, I could pull it out of the limit, figure out that this is going to 0, and then multiply 100 billion by 0, it's still going to be 0. That make sense? So the constant up top doesn't really matter. What matters is that it's fixed. It's not moving. This will work for any power of x as long as the power is positive integer. What if it's negative? What if I have limit x goes to infinity of 1 over x to the negative 2? Is that 0? No. That's not a positive number, right? In fact, I should have put 0 up here. That one was 0. This one was 0 up there. In fact, if you rewrite this problem, isn't 1 over x to the negative 2 the same as x to the positive 2? Isn't that what that means? Now let x get huge. What happens if x gets big here? Doesn't that number just get huge? Just becomes infinite, doesn't it? Think about it this way. If I'm letting x become infinitely large, and then I'm squaring it, isn't that still getting even larger? So this answer would be infinity, not 0. Make sense? Now, this is a major concept here. The idea of letting x become arbitrarily large. Now let's do some of the problems that are appearing here. So first one I'm going to do is this one here. I'll zoom in on it. We're going to find the limit as x goes to infinity of 3x squared plus 2x minus 5 over negative 4x squared plus 7. Let me see if I have my notes. Oh, here they are. Limit x goes to infinity, 3x squared plus 2x minus 5 over negative 4x squared plus 7. What was it that we did anytime we wanted to calculate a limit? What did I say we always did first? Just plug in. We called that direct substitution, right? Let's just try direct substitution. So I put an arrow. I get 3 times infinity squared plus 2 times infinity, right? Minus 5 over negative 4 times infinity squared. Now, the math gods are kind of pissed off at me right now because this isn't really allowed, okay? Infinity is not a number, right? Infinity is not a number. Do we all agree with that? Right? If infinity was a number, that I could find it on the number line. No matter where I go on the number line, I can always find something bigger than that. So just add 1 to it, right? So there is no final number. So infinity is an idea, right? It's a concept. So I can't plug it in, but I can think about it. I can say, if I take a huge number, infinity, and I square it, what's that going to be? A huger number, right? Is that a good word? Huger? It's the hugerous number. It's a big positive number, right? I multiply it times 3, and what do I get? It's even bigger. So this right here, I'm going to draw an arrow below that. That's headed towards infinity, isn't it? The top left corner is still infinite. Plus what? 2 times infinity, which is still infinity. It's still infinite. Again, I'm not saying that these are equal, okay? I'm just saying the idea is that that's getting huge, plus that's getting huge, minus what? Do you think taking 5 away has any effect on infinity? No, because that thing's just getting bigger and bigger. Taking away 5 is like, come on, it's like a fly. Just get out of here. Just a nuisance, right? Doesn't affect it. Then over what? Infinity squared is infinity, but then negative that should be negative infinity, shouldn't it? But negative infinity is not a small number, right? It's a huge negative number, right? On the x-axis, infinity is way to the right, negative infinity is way to the left. And then I have what, plus 7? Do you think that has any effect on it? No. So really what's happening is the top is headed to what? That negative 5 doesn't matter. Infinity plus infinity? To infinity, yeah, it's still infinity, right? Infinite over negative infinity. So, what do you think? Negative 1? I mean, you want to say maybe negative 1, but the problem is the infinity on top is not the infinity on the bottom necessarily. It's just what we're trying to say is this. Really, at the end of it, what we're trying to say is the top's getting big and it's positive. The bottom is getting very big and it's negative. And the question is, does it head somewhere? Right? Like in the picture we had with the 1 over x, it went to 0, right? The other one, it went to 0. Does this head somewhere? Does this graph head somewhere? Now, how many of you remember rational functions? Rational functions, college algebra. When you found horizontal asymptotes. Anyone remember that? What we did, I don't know if you remember this, you look at the power up here and the power down here. Tell me if this rings a bell. If the powers are the same, you took the 3 in front and divided by the negative 4 here, and that was your horizontal asymptote. How many of you learned that way? Yeah? Okay. That's what I'm about to do, but I'm not doing it that way. I'm doing it the calculus way. Okay, here's the way the calculus is going to work, and this is going to be kind of cool. So what does this mean to us right now? It means this is a bad thing. That means we're going to need to do some algebra or a trick. So for us in this class, from here on out, if we ever see 0 over 0, we need to do something, right? If we see infinity over infinity, or infinity over negative infinity, or negative infinity over negative infinity, any combination of infinity over infinity, we're going to have to do something about it. The standard trick for this situation, when you have a polynomial and a polynomial like this, is to come in and divide everything by the highest power of x you see in the denominator. What's the highest power of x I see in the denominator? X squared, right? That's the highest power. So watch the way I'm going to do this. I'm going to write limit. X goes to infinity. I'm leaving a little space, rewriting the problem. And I'm going to multiply the top and bottom by 1 over x squared. Because what's 1 over x squared over 1 over x squared? That's a 1, so I haven't changed the integrity of the problem at all. But this has the effect, when I distribute it through, of basically dividing every term by x squared, doesn't it? 1 over x squared times this divides it by x squared. 1 over x squared times this divides it by x squared. And the same thing on top. So let's go ahead and distribute through. Everyone understand I have to distribute like this? So my new limit, also notice I'm keeping my limit, right? I have not let x become infinitely large yet. What happens on this top right multiplication? 1 over x squared times 3x squared. What happens there? What do you get? Just 3, right? The x squareds cancel. So I get 3. What happens when I multiply the 2x times 1 over x squared? It's 2 over x squared, right? One of the x's cancels. You get 2 over x. I'm not showing this. I'm hoping you're holding on and that you understand where these are coming from. I'm distributing. What happens when I do negative 5 on top of x squared? I just get negative 5 over x squared, right? Okay, all of this divided by, now the same thing on the bottom. What's 1 over x squared times negative 4x squared? Negative 4. And then what's positive 7 times 1 over x squared? 7 over x squared. Now why the hell would I do that? Why would I do that? Just for fun? Let x go to infinity now. Okay? Let x go to infinity. What happens to this when x goes to infinity? Nothing. You don't see an x there, do you? Right? There's no x here, so x being infinite doesn't have any effect on this, right? What happens to this when x goes to infinity? It goes to 0, doesn't it? Because you have a fixed number 2 over a number that's becoming infinite. That's going to go to 0, right? What's going to happen here? Fixed over infinity, right? That's going to go to 0. Bottom left, negative 4 is not changed. Fixed over infinity, 0. So notice the limit's going to go away now because I'm letting x go to infinity. I'm realizing this are all going to go to 0, right? They're all approaching 0, which leaves me with just 3 over negative 4. And that's the limit. Which is what you would have gotten had you just done in college algebra, the 3 over negative 4, right? Look at it. So you might be asking yourself, well, why would we want to do this, right? Would you be asking that or no? You would? Okay, let me show you why. Any questions on this example? Okay, good question. Why did I pick 1 over x squared? Because whenever we have a polynomial in the denominator, we want to use as our 1 over here. The reason I picked x squared here was because I want to pick the highest power of x that I see in the denominator. Why? Why do I do that? Because what's always going to happen on this first multiplication right here, if this is the same power as this one, it'll cancel out and I'll be left with just a number, right? And that number will not be affected by x, which means when I let x go to infinity, this will not be 0, so I will not have division by 0. Does that make any sense at all? Okay, that's why we do it. Yes? Let x go to infinity here. Go, go, go. Talk to me about what's going on with direct substitution. Where's the top headed? Infinity. Is it okay if I just put infinity up there now? Everyone understands 3 times infinity is infinity, plus 1 is still infinity. So we have infinity on top. On the bottom, all this in here is infinite, right? Square root of infinity gets smaller, but hey, infinity is still getting big, so eventually it just still is infinite, right? So we still have infinity here. We have infinity over infinity. That is now to us a situation that requires some algebra or some sort of trick, all right? Bad situation. Time to do some work. Algebra, trick. Yes? When you have infinity, direct substitution could work, yes, it could. We're just looking for infinity over infinity as being when we need to do something. Like I gave you this problem right here, this one right here, where I said let x go to infinity of 1 over x to negative 2, and we said, oh, but that's just x squared. And then you plugged it in, and you said, oh, well, that's just infinity. Like, that worked, right? We got an answer. Infinity is infinity, right? So we can just say, the thing is, what's infinity divided by infinity? That we don't know. I guess you could think about it this way. If I tell you that I have a really big number and I'm dividing it by a really big number, can you tell me anything about the answer? It would all depend on the numbers, right? But if I say I have a really big number, then you could tell me it's a really big number, right? It's the division that kind of causes the gray area. That's why we can't determine what it is. I hope that made sense. I'm hoping a lot of things make sense. Okay, so what was the trick I said we would want to do here? We want to try and come through with the highest power of x we see on the bottom, right? The highest power we see on the bottom is what I said. That's if this is a polynomial, but that's not a polynomial because it's underneath the square root. Yeah. Well, yeah, the conjugate, you need two terms for the conjugate. So how about I do it this way? How about I approach it this way? The goal was to try and kill the x squared off, right? That was the goal. Try and kill off that x squared so that when I canceled it, I would have just that 4 left there. That's the goal. The problem is that whatever I put out here has to go on the top and bottom, doesn't it? And that means it must go into the square root. This is an algebraic operation I have to do. I have to pass this into the square root and then let it go, let it get in there and then start doing what it needs to do. My question to you is, what happens to things when they go in square roots? Kind of. Let's do it this way. If I said, what's the square root of 4x to the 6th, what would you tell me? You would say, okay, what's the square root of 4, right? And let's do it this way. I'll put a y out here. Let's do that. Put that y there. You would say, okay, the square root of 4 is 2, so I bring that out, right? And then you would say x to the 6th, well, how many times can I get 2 into 6? 3 times. So you would say, I'm going to pull an x cubed out, right? And then the y you couldn't do anything with, right? So you'd leave it like this. Y'all agree with that? Okay, that's how you pull things out of roots. Now, if I told you to take this and push this back into the root, what would you have to do? Square it to put it back in, right? You would have to turn that 2 into a 4 and turn that x cubed into an x to the 6th. So I need to choose something out here so that when I push it in there, it's going to kill off x squared, which means I should use what? And don't worry about the 4. I just want to kill off x squared. Just 1 over x, right? 1 over x. Let me write it down, and maybe everyone will see it. If I write 1 over x on top, over 1 over x on the bottom, now we still have this here, 3x plus 1, then the root, 4x squared plus x plus 1. Does everyone see that if I take the 1 over x and I push it into the root, it's going to get squared on its way in? When you square 1 over x, you get 1 over x squared, don't you? Yes. That goes in the root, gets 1 over x squared. So my next line would look like this. I'll leave the top for now. I have the square root, and the 1 over x went inside, became 1 over x squared. Once it's inside, it can pass through all the terms. Make sense? 1 over x goes in as 1 over x squared, and then I'll pass it through each of these. What do I have on top? I'm not taking the limit yet. What do I have when I distribute 1 over x through on the top? 3 plus 1 over x. Good. Over on the bottom, I have a square root, don't I? And then 4 plus 1 over x plus 1 over x squared. That was me distributing this 1 over x squared through to the 3 terms here. You see why you cannot use 1 over x squared out here. Because when it would go in, it would become 1 over x to the 4th. And what would be wrong with that? If this was 1 over x to the 4th, then this would have an x on the bottom, wouldn't it, still? And then when you let x go to infinity, you get 0, 0, 0, and then you have division by 0. It's no good. Now I will let x go to infinity, and what do I get on the top? This will go away, right? Fixed over infinity, so I'll have 3 over what? Gone, gone. Those both go to 0. So square root of 4 is 2. Answer is 3/2. Questions, questions? I'm going to give you another example. Limit x goes to infinity, x cubed plus 2x over 10x squared plus 1. What do we have here? Where's it headed? Infinity on top, right? Over infinity on the bottom also. So we need to do something. Do we have a polynomial in the denominator? Yes. So I can come through with what on top and bottom here? 1 over x squared, right? I don't have a root now, so I can just do it, right? 1 over x squared. All right, let's do it. Nope, not at all. Could you? Yes. Do you need to? No. Because all I'm caring about is killing off the x squared on the bottom. That's my primary concern. Go ahead and distribute through. What would you get if you distribute through? Does anyone have a question on what I did? Good. So what's 1 over x squared times x cubed? That's x cubed over x squared, isn't it? So it'd just be x, right? It's just x. Then what? Plus, I'm doing this one right now. 1 over x, but the 2, we have a 2 there, right? 2 over x? 2 over x. And then on the bottom, 10, and then 1 over x squared. I really do hope that what you're noticing is that by using this technique, we're always leaving ourselves something on the bottom that's not going to be 0. So we're not going to get division by 0. Okay, something weird happens. X goes to infinity. What happens right here? X is infinity, right? So I have what? Infinity plus, where does this go? Fixed over infinity goes to 0 over 10 plus 0, right? Which is really like infinity over what? 10. What do you think that's headed towards? Infinity. Infinity. Right? You've got a number that's getting bigger and bigger and bigger and bigger on top. The bottom's just staying 10 the whole time. So this fraction gets bigger. Do you agree? You could also have written it this way. That's 1/10 times infinity. That's the same thing. 10 divided by, or infinity divided by 10 is a tenth of infinity. A tenth of infinity is still infinity. So the answer is infinity. The answer is infinity. That means if you graph this, as you go out to the right, what's the graph doing? It's going up, right? So again, you may go back to college algebra. You might remember that when you had a rational function, if the degree of the top was bigger than the degree of the bottom, then on the right side it either went up forever or down forever, and that's really what's happening here. All right. Y'all like this? Like's too strong of a word? You love it. Infinity. Yep. Infinity. I'll put this in parentheses just to stress that you're taking the limit of the whole thing. This one doesn't look very ominous at all, but we need to talk about it. Where's it going? Direct substitution. Infinity cubed, which is infinity, right? Minus infinity. What do you think? 0? Kind of like infinity over infinity was 1. See, we don't know how big the infinity was, right, on top and bottom. So again, we have no way of judging what that ratio is. Here, infinity minus infinity is like me saying, again, I have this huge number, and I'm subtracting another huge number, but I'm not telling you they're the same number. They're just huge numbers. You have no way of telling me what the answer is, right? So this, again, is something we cannot determine. This is a bad situation, and therefore we're going to have to do some sort of algebra or some sort of trick. Now, before I do that, would this have been a problem? Direct substitution here would have been infinity plus infinity, right? So what's a huge number plus another huge number? Huge number. So this answer would have been infinity. Okay? The answer here would have been infinity. We would have boxed it up. It's the subtraction we can't determine. Well, I see what you're saying. Like get 1 over x out here. In the previous problems when we did that, keep in mind that when we actually did this, whatever we did to the top and the bottom at the same time, because this is a 1. We can't just come in here on this problem and just put 1 over x here. Because if you just put 1 over x, you're actually changing the problem. 1 over x is not 1. So let me just show you how it's going to happen. Or, yeah, why don't we factor? Look, check this out. Why don't I do this? Take that problem. This one is its own problem. We're done with it. Why don't I factor an x out? If I factor an x out, I'm left with what? X squared minus 1. Now do direct substitution. Where does x go? Infinity. But then I have what? Times, right? This is multiplication. What's infinity squared minus 1? Infinity. What's a huge number times another huge number? Huge number. So the answer is what? Infinity. Now be careful, because what I'm not saying is I'm not saying infinity minus infinity is always infinity. I'm saying in this particular problem, This infinity, think about it, x cubed, take away x squared. Isn't x cubed getting big really fast? Like if I give you a number, I tell you to cube it, it gets really big, right? If then I say come in and subtract x, that's not going to be as big as this one, right? Let's say 10. What's 10 cubed? Okay, 10,000? 1,000? How about 2 cubed? Whatever. Okay, so 8, take away 2 would be 6. Then if you did 4 cubed, 64, take away 4, you're now at 60. Then you do 5 cubed, 125, you take away 5, you're now at 120. So what's happening? It's getting bigger and bigger. It's because the x cubed completely overpowers the x term, and the difference becomes infinite. Yeah? But not every problem will work that way. So I just don't want you saying, oh yeah, anytime I see infinity minus infinity, the answer is infinity. You have to work each problem out. Let me give you another example. What would limit x goes to infinity of the square root of x minus, you know what, let's make it the cube root of x minus the square root of x be? Well, that's definitely going to infinity, right? Cube root of infinity is still infinity. We're taking away infinity again, and this is something I don't know, so I need to do something to it. Yes? So I need to do something to that, try and figure out what the hell that is. In the previous problem, we factored, didn't we? And that seemed to work out okay. Actually, it worked out really good, right? Anytime we can convert something to multiplication, can't we always tell what it's going to be, pretty much? Well, not always, but if that's infinity times infinity, my answer is infinity. What if one of these was negative? You would get negative infinity, right? What if they were both negative infinities? It'd be positive infinity. Okay, so, but here, how do I convert this to multiplication? Well, let me show you how you can do it. This can be a little tricky. The cube root of x is the same as x to the 1/3. The square root of x is the same as x to the 1/2. You buy that? That's what that means? Cube root of x. These are what we call rational exponents. Now what I'm going to do is I'm going to look at both of these fractions, and I'm going to rewrite the fractions, but with common denominators. So what would be a common denominator between 3 and 2? 6. So could I rewrite it this way? Keeping the limit here. 6. So x to the 2/6. That's still x to the 1/3, isn't it? Minus x to the 3/6. Do you agree with that? Now, why am I doing this? Trying to find something in common with both of these. I think the best way to show you this, or to explain it, is to show you. If I pulled out an x to the 2/6, what would I have? Notice I pulled the smaller of the two fractions out. 2/6 is smaller than 3/6. How would I get these two terms back? What do I multiply x to the 2/6 by to get back x to the 2/6? 1. Okay. Minus, what do I multiply x to the 2/6 by to get x to the 3/6? X to the 1/6. Now the reason why is because when you multiply x to the 2/6 times x to the 1/6, you add the exponents. 2/6 plus 1/6 is 3/6. Yeah? Yes? That's tricky, isn't it? I mean, that is tricky. You have to rewrite the radicals in rational exponents. You have to find a common denominator. You have to look at the smaller one, factor it out, and then kind of recreate what you would need to make that happen. But now what I've done is I've created multiplication. Yes. Rewrite this with the 6 down here, which means I have to multiply top and bottom by 2. Rewrite this one with the 6, multiply top and bottom by 3. Follow it? Okay. Now just for hopefully for clarity, this really means the 2/6 was really 1/3, wasn't it? So I could write this that we're at the cube root of x times 1 minus the what? What root is this? 6th root of x? Negative infinity is going to be our answer. Now let's see why. This one, when I let x go to infinity, the cube root of infinity is infinity. But now I have multiplication. I let x go to infinity. This one becomes 1 minus infinity. 1 minus infinity is negative infinity. Positive infinity times negative infinity is negative infinity. So our answer is negative infinity, and we box it up, and we're happy campers. How about this? What are a and b in this problem? They're just constants. They're just numbers that we don't know. So like it could be a 4x and a 10x. We're not given that in the problem, so we just assume throughout the problem that they're just numbers we don't know. All right? But they're fixed. They're not changing. The only thing that's changing in this problem is x. It's getting huge. So what is the form of the limit that we have when we let x go to infinity? So the inside here, x squared, is infinity squared plus what? A times infinity should still be infinity. So infinity here, square root of infinity is infinity. So we have infinity minus, again, infinity. You all agree? And if on a test you put 0 and move on, how many points out of 10 do you think you'll get? 0. I usually give 1 just because you showed up for the test. But if you do infinity minus infinity is 0, that's almost no credit. Do you understand why I would take off that much for that? Okay. So we need to do something here. Now in the previous problem, we were able to factor something out, right? And the reason we were able to do that is because we could look at both of these as just powers of x, right? And in the one before that, we looked at these are just powers of x, and we factored an x out. This problem, we don't have just powers of x because you've got some other crap under there with it, right? So we have radicals, right? We have two radicals separated by subtraction. What have we done in the past when we have radicals and we're stuck? The conjugate, right? The conjugate. But watch, the way you bring the conjugate in here, you have to be very careful with it. What is the conjugate of this thing? It's all that with what between them? Plus, right? So watch the way I write this, okay? Here's my original problem. Here comes my conjugate. Now, I can't just multiply by the conjugate, right, out of nowhere. I can only multiply by 1. So I have to put the conjugate over what? Itself. That's all right. We're not worried. Over itself. And then on the other one, can we just throw that whole thing over 1 and be happy? So the blue is the original problem. I don't know if that really looks blue to you or not, but blue, and then over here, this is the conjugate I'm coming in with, which is my 1. We should get some good things to happen up top. Anytime we come with the conjugate, the middle terms go away, right? All we get are the outside ones squared. So this will become, I'm just going to show the outside ones. This times this, the root goes away, so I'm left with, and I'm bringing the limit with me, becomes what? X squared plus AX. And then the middle ones go away, I get this last one, right? Now be extremely careful here, because when I do this one times this one, the root is going to go away, yes? But what's the sign? It's negative, so that negative is going to have to pass through that new radicand. So I'm going to put a negative here, and I'll put it in parentheses, the x squared plus bx. All of that over conjugate, conjugate. Questions? Did this help at all? Let's see. What do we get? Limit. Do you see what we can cancel in the top? The x squareds are going to cancel. So what's still there? AX minus BX over square root of x squared plus AX minus, or plus, that's a big deal. X squared plus BX. I'm not sure that we gained anything there, did we? Let's see. What's happening on top? We get infinity here. A times infinity should be infinity, minus b times infinity should be infinity. Infinity minus infinity is, I don't know, right? But how about this? How about if we look at this top here real quick? Just pull an x out real quick. Do you agree that that goes to infinity, x, right? And a minus b, those are the two constants, right? A minus b is either positive or a minus b is either negative. One or the other. So I know the top is either going to positive or negative infinity. I don't know which one, but it's one of those two. Do you all follow the logic there? So the top here is going to positive or negative infinity. I'm going to put plus or minus infinity. I don't know. Over, what's the bottom going to? Infinity, this time though, plus infinity, right? Which is infinity. So I have infinity over infinity, which is not a good thing, right? But we have a way of dealing with infinity over infinity. Do you remember what we did? We looked at the highest power and tried to deal with it, right? Like this thing. So what we've done, just trying to recap, because we're not done, right? Just trying to recap where we were. We started the problem, we were in infinity minus infinity, we didn't know what to do. We did all this conjugate crap, and now we're at infinity over infinity, which is actually a better situation to be in than infinity minus infinity is. So what am I going to do? Yeah, I want to kill off the x squared here, and there's an x squared here too, right? So I'm going to kill off x squared. It's underneath the root, so I come in with 1 over x on the top and bottom. 1 over x. So when it goes in, it gets squared. Okay. So we're going to have limit x goes to infinity. I'm coming in with the 1 over x on the top, coming in with the 1 over x on the bottom. That's going to distribute through to that x times a minus b over the bottom, which was square root x squared plus ax plus square root x squared plus bx. Are you saying why are we not using x squared? Yeah, because we're trying to kill off x squared, but it's in a root, so when it goes in, it's going to have to be. If you want another way of looking at it, if you don't want to have to think through it too much, if you're trying to kill off x squared, right, and it's under root, just take the square root of x squared. What's square root of x squared? X. That's what you'll come in with. 1 over x, 1 over x. All right, let's pass this thing through. This multiplication just kills off that x, doesn't it? I'm just left with limit x goes to infinity a minus b over. When this 1 over x goes in here, it gets squared, so that becomes square root of 1 plus, when that 1 over x goes in here, it becomes 1 over squared, but then it gets put under here, just a over x, right? Because you had ax there. You're dividing it by x squared, not x, right? Yes? And then we have still down there plus. Now what about the other root? Because the other root gets to play too. That 1 over x goes into that root also. 1 plus b over x. Good. Questions? Now, let x go to infinity. Any effect on the top? Nope. The bottom? That goes to 0 there, a over x. b over x also goes to 0 because that's a fixed over infinity. So we get square root of 1 plus the square root of 1, which is 2. So the answer is a minus b over 2. Notice when my limit went away, right? I stopped writing the limit as soon as I finally let x go to infinity. How many examples have I done so far here? There's 8, 6, 8, whatever. Do you see why I'm saying on the test on Wednesday, this has a lot more that I can give you. On the 1.5 section, you'll probably have 1 or 2 problems at the most. This is a good variety of things that you could see here, right? We okay? It keeps coming, okay? So here we go. Limit x goes to infinity of sine of 1 over x. Yeah, I meant to say infinity. I apologize. I said infinity. I wrote 0. I told you all about lazy 8, right? Yeah, see. You're allowed to use that joke whenever you want, when you're out with your friends doing stuff. That's cool with me. Direct substitution. Sine of 0, right? Because this thing's going to 0. What's sine of 0? 0. The sine of 0 is 0. How do we know that? Just go to the sine function, right? Here's sine. That's what it looks like. What's happening at 0? It's 0. What would this be? Limit x goes to infinity cosine 1 over x squared. 1. Because that's going to cosine 0, which is 1. How about limit x goes to 0, and I mean 0, sine x over x. Drum roll. What? 1. Yeah, that's the one everyone's supposed to know last class. Remember? That's 1, right? Why? Why is that true? Because I said it was true, and I said we'd prove it later, and just everyone needs to know that, right? Right? That's what we said. Now, compare that to this versus limit x now goes to infinity of sine x over x. Now, we have not seen something like this yet. We've not seen something like this yet, so that's why I'm showing it to you. Direct substitution. Let's start with the bottom. Where's the bottom headed? Infinity. Okay. The top is headed to sine of infinity? The heck does that mean? Sine of infinity. Right? What is this? What we're really asking ourselves there is, what is the sine function doing as you go to infinity? So let me draw it. It's fluctuating, yes, exactly. What it's doing is it's starting at 0, and then it just does this and just keeps doing that, right? Repeats itself forever. So if I ask you right now, where's the sine function going as I go out to infinity, you're going to tell me, well, it just keeps going back and forth, right? Like, it's not going to one place, right? It's not going to one particular place. Agreed? So does that mean that we say this limit does not exist? Well, you would think so, but it does. And here's the reason why. Do you agree? See if you can follow the algebra, the logic here. Does everybody in this class agree that no matter what, sine is always bounded between -1 and +1? Does everyone agree with that? Yes? Everyone agree with this? No matter what the value of x I ever plug into sine, it's always got to be between -1 and 1. Now, if I divide everything, both sides of the, all the terms of this inequality string here, by x, that means if sine was stuck between -1 and 1, then sine x over x should be stuck between -1 over x and 1 over x. Do you believe that? Do you believe that? That's true? Now what I'd like to do is I'd like to ask you, what happens if I take that and I take the limit as x goes to infinity? It goes to 0, doesn't it? I'm going to put an arrow here. That goes to 0, right? And if I take the limit of this one as x goes to infinity, where does that one go? 0. So if I ask myself in the middle, what happens as x goes to infinity, it's got to be stuck between those two answers, right? It's got to get, whatever this limit is in the middle, is stuck between the two limits on the outside. But what are the two limits on the outside? 0, which means that limit in the middle must also go to 0. This is what's known as the squeeze theorem. If you ever want to try and figure out what's happening is something you really just can't tell, you try and squeeze it between two answers. And if the only number between 0 and 0 is 0 itself. That's the algebraic way of explaining it to you, all right? That's the algebraic kind of like, that's how we do it. But now I'm going to just show it to you a different way, like more of just a logical, let's look at the graph type way. Can I move to a new page? What's that? The limit is 0, yes. But I'm going to show it to you a different way. How about this? Remember we said this? Remember we said fixed over infinity, that would head to 0? Remember that? And I boxed it. I said that's very important. Yes? What I would like for us to add to this is this idea. If you have a bounded numerator over infinity, it's going to be going to 0. Yeah, let's talk about what I mean by bounded. Of course, if it's fixed, it makes sense to us, right? You take a number, 10, and start dividing it by bigger numbers, it's going to get small. But what if I tell you the numerator is not fixed? It's not 10, but it always stays between two numbers. Like the sine function, right? The sine always stays between -1 and +1. So what's the worst case scenario? If the sine's up here, right, the biggest it could be would be 1, right? Which would be fixed. 1 divided by a big number is going to go to what? 0, right? And then if I take -1, it's still fixed number divided by infinity is still going to go to 0. So the worst case that could happen with the bounded function is that I have a maximum highest value it could be, but that doesn't matter because the bottom is getting so big it's going to overwhelm it. Does that kind of make sense? So what we want to do is kind of add to this whole logic. It's two scenarios. If we have a fixed or bounded function divided by something that gets big, it's always going to go to 0. What would be some other functions that are bounded? Cosine, right? Cosine's bounded. Is tangent bounded? Tangent is not. Cotangent is. So those are, you kind of follow what I'm saying there? We will have to kind of recognize problems like this, like limit x goes to infinity, cosine x over x. That would be 0 because we have a bounded function on top, right? Bounded on top, divided by infinity on the bottom. So that's 0. Now what about this one? Limit x goes to infinity of just cosine x. Just cosine x. What is cosine doing as I go out to infinity? Same thing the sine was, right? But this time I'm not dividing it by anything, am I? So I'm asking you, where is cosine headed? It's not, right? It's going up and down. Since it's not headed to anywhere in particular, and there's nothing trying to divide this out, this one would be does not exist. Does not exist. Do you see the difference between the two problems? The top one says, oh, I've got this thing, it's oscillating, but it's bounded, always between -1 and 1. And the bottom just keeps getting bigger. It's just going to start squashing this down to nothing. And then we have this one, which is cosine is just going up and down, and there's nothing squashing. It just keeps on going up and down. So I say, where's it headed? And you're like, shit, I don't know. It's 1. No, it's -1. Well, it keeps on going back. So you can't nail it down to anything. So you have to say it doesn't exist. I'd like to show you a graph. I'm going to use a program that I have that is free, WinPlot. I think I showed this to you one time before. I'd like to show you that cosine x that we had just a second ago divided by x. What did we say it was going to do? Cosine x over x as x went to infinity. We said it was going to go to where? 0. That's it right there. Kind of hard to see it, but it's kind of like cosine, right? Kind of. But what's happening to it as you keep going out? It's getting smaller. You could even look at it this way. That's 1 over x times cosine x. What was in pre-cal the number in front of the trig function? In front of sine or cosine, what was that number? It gave us the what of the function? Amplitude, right? So this number right here, that amplitude is getting what? As x goes to infinity, the amplitude's what? Getting smaller. So it's trying to draw the cosine curve with smaller and smaller and smaller and smaller amplitudes. Now, why would a function like that be important or useful? Think of a cosine function as a bouncing ball, right? You let a ball go, it bounces, comes back up, bounces, comes back up, right? Back and forth. Cosine function models that pretty well, but we actually know if we drop a ball, it doesn't come up to the same height, right? The next time it's a little lower, and then a little lower, and then a little lower, 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 until it's pretty much stopped, right? The function I just graphed is a much better representation of a bouncing ball. Would you agree? Right? Let the ball go, right? Bounces, starts at a height, hits the ground. This is like time. Hits the ground, doesn't go below the ground, but then comes back up, not as high, then not as high the next time, not as high, and then. So that would be much more interesting to study than just a regular cosine function would be. That's about half of the information for this section. Are y'all ready to at least start the next half for 1.6? This section's real. That's why I thought it was important to get at it today. Wouldn't you hate for this to all be the stuff you're seeing on Monday and you have a test 48 hours later? At least you'll go home and be able to practice this, right? All right, so what we have so far is fixed over infinity is 0, bounded over infinity is 0. But what happens if we get a fixed number? So this is what we're going to look at now. What happens if we get a fixed number over 0? I think we started today with this, didn't we? Someone asked me a question about the homework. I said, what happens if we get 5 over 0? We're going to have to deal with that today, right? I'm ready to deal with it, all right? Well, let's just start with some examples. What if I had 10 and I divide it by 1? What's that equal to? 10? Now let's let the bottom get smaller. What's 10 divided by a half? So do the reciprocal. The 1/2 flips up and it gives you what? 20, doesn't it? 20? So this is bigger, isn't it? And then what if I do 10 divided by an even smaller number, 1/4? What would that be? 40. So that would be bigger. And let the bottom keep getting smaller and smaller. So 10 divided by 1/8 would be 80. That's even bigger. And we keep letting that get smaller and smaller and smaller. It starts to blow up, doesn't it? Becomes infinitely large. So this is approaching infinity, yes? But, what if it was negative 10, negative 10, negative 10, negative 10? Then it would have been negative infinity, right? So it could possibly be positive or negative infinity depending on the sign of things. See, in the previous one where we had fixed over infinity, it didn't matter because when you approach 0, 0 is 0. 0 doesn't have a sign. It's not positive or negative, right? But when we're going this way, we're approaching a number that's either going to be positive or negative. So we have to account for that. Here's a graph. We looked at this a while back. Today, f of x was 1 over x squared. I don't want to bring it up again, but it looked like this, right? What was the limit as x approached 0 of this one? What did we say the answer was? Infinity, right? Because as you come in from the left and the right, it goes to positive infinity. Let's try and understand why it's infinity without the graph now. Okay, how could we figure this out without the graph? Well, what's the top? Fixed, right? What's the bottom? Where's it headed? It's 0, but the fact that it's squared, right, means that it's always a positive number. Right? The bottom is always positive, and the numerator is 1. Yes? So it's always positive also. So what I really have in this scenario is a fixed number on top, which is positive. I'm going to do a little plus sign, over something that is headed towards 0, right? But positive also. Whenever you have fixed over 0, it can either be positive or negative infinity, right? But if the top's positive and the bottom's positive, then it must be positive infinity. Why is the bottom positive again? Because it's squared. So the answer here would be positive infinity. See, I'm trying to show you that right over here on the right side without the picture. I just brought you the picture to remind you what our answer should be. I want to do another one. How about this one? What's the limit as x approaches 0 of 1 over x? Do I remember what this one looked like? You remember what it looks like? What was the answer to this? You remember? It was does not exist. Because from one side it was negative infinity, the other side it was positive. But how are we going to do that without a graph? How are we going to figure that out? So, you ready to watch? Right now, if I just try and plug in 0, what's the form that I have? Fixed, right, on top. And I'm even going to add to that that it's positive. Over what? Where's the bottom headed? 0. Is it headed towards 0? Is it going to always be positive or negative or what? That's right. That's the key. Because we're doing the limit as x approaches 0, and I'm not saying which side, you have to look at both, don't you? If you come into 0 and get used to seeing this, I'm writing a number line here to kind of help aid me in thinking through this. If I approach 0 from the left, those numbers are what? Negative, right? So then I would say, okay, this is negative, right? But if I approach from the right, those little numbers are what? Little positive numbers. Which means that if I come in from the left, my answer would be negative infinity. If I came in from the right, my answer would be positive infinity. Understand the difference between those or not? Y'all are just like, this was our graph. Right? As we came in from the left, it went to negative infinity. From the right, it went to positive infinity. So since they're different, my answer would be does not exist. What if I had specified in the limit which side? Then yes, you would have been able to give me an answer. You exhausted? I'm starting to feel exhausted. Limit x approaches 3 from the left of x. Oh, no, not x. Yeah, no. X plus 1 over 3 minus x. Great example of a test problem right here. All of them today have been great examples of test problems, but I said we have kind of two topics today. This is our first one from our new topic, and a good problem for a test. Okay, direct substitution. Where's the top headed? Remember, this is 3, right? And you're approaching from which side? The left. This is not -3, right? So I'm approaching 3 from left. So it's just plug in 3, right? 3 plus 1 is 4. So I'm going to write this over here. I have a fixed, positive number up here? Over. Now on the bottom, where am I headed? 3 minus 3 is headed towards 0, isn't it? Well, I know it's headed towards 0. So I know that I could possibly get positive infinity or negative infinity, right? And it could also be does not exist, because we just had it does not exist. And when I summarize all this, I'll just remind you that there's 3 possibilities. When you have fixed over infinity, there's 3 possibilities. Positive infinity, negative infinity, does not exist. Those are the only 3 outcomes. So how can I determine what the bottom's doing? Come from the left. So I suggest you draw a number line. Here's 3, right? I'm coming in from the left. Somebody give me an example of a number that is to the left of 3. 2.9. How about that? That's close to 3, kind of. If I were to take 2.9 and plug it in right here, what's 3 minus 2.9? A positive number, though, right? That's the key. It's positive. And if I get even closer, 2.99, 3 minus 2.99 is still a positive number. They're getting smaller, right? Getting closer to 0, but they're positive. So I can conclude here that coming in from the left, I get positive numbers. Look, there's no work that you have to show here. That's the thing most students on tests don't know, like, what do I have to show? I suggest you draw a number line. Give me some examples of the numbers you're plugging in mentally to convince yourself it's positive. Because if you just flip a coin and don't show any work and it's wrong, then it's going to be wrong. So what is the answer? Positive infinity. Here's a tricky one. What's the limit as x approaches -3 from the left of 4 plus x squared over x plus 3? Okay, direct substitution. What's 4 plus, what am I plugging in? -3. -3 squared is 9, so 4 plus 9 is 13. So I have a fixed positive number, right? Whoa. Will it always be fixed positive? No. Could be fixed negative. And then on the bottom, -3 plus 3 is 0. So I know right now it can be infinity, negative infinity, or does not exist. So I'll go to a number line. I'll draw -3, and I will approach it from the left side. So what's a good example of a number over here? I see why I said this is going to be tricky. I want to make sure everyone understands this. -3.1. Right? -2.9 is on this side, on the right side. The left side is a little bigger, right? Because the next number over here would be -4, wouldn't it? And over here would be -2. Over here somewhere is 0. So what happens if I take -3.1 and plug it in right here? -3.1 plus 3, that will be a negative number, right? And therefore, I know the bottom's going to 0 through negative numbers. So I can say these are negative, which means I have 0, negative. And so I know my answer is a positive divided by a negative, which would be negative, infinity. You're just going to have to mess with those. I would recommend, though, that you do this whole number line thing, because that really helps me see that you understand what you're doing with it, and it keeps you from getting into some tough positions on those. Okay. The order that I presented the material today is actually kind of backwards from the way it's presented in the book. So your homework assignment will actually start with this stuff and then go into the other stuff later. I anticipate you're going to run into some issues, but I think what you should do for homework is page 68. So don't do what's on that handout thing down there, okay, on your schedule. Just don't worry about that. 13 through 32. I didn't. I suggest you do all those problems. Start with the odds and then work through the evens. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think we're missing one person. Is Brooke here? Dang it. Not dang it like you're here, but trying to figure out who's missing. How about Kyle? Kyle Keller? Yes. Okay, everyone can go. Oh, you just didn't sign in? Okay. I believe so. Okay, no worries. Let me turn off my video so in case I have to cuss at you or something.